Now we have to switch to another formulation. With it is the index or component notation. And in component notation, I just, instead of a vector, for example here B, I write each component, and each component I write with an index. So each index here takes values 1 to 3. 1 is the first, second, 2 the second, 3 the third component. The cross product becomes an epsilon symbol. This is completely antisymmetric in I, J, and K. And all repeated indices are summed over. This is the Einstein summation convention. So this is exactly the same information. And what you see in red, this is now the important point about the pre-metric. This is where the metric appears, the space-time metric. It says how we measure distances in our space. It is the quantity that carries information about the local characteristics of our space, and also about the choice of our coordinates. This is encoded in this object. And it appears here hidden as a covariant derivative. These are not plane derivatives, because plane derivatives will not be invariant, but these are covariant. And here, in the free space relation, it appears because D has an index upstairs and E has an index downstairs, and this is important. These are two different objects. One's a vector, the other one is a covector. You can imagine this as row vector and column vector, and that's not the same thing. And the object that somehow communicates between the two, this is also the metric. Okay, and now the aim is get rid of all traces of the metric. Why? You saw before that we have the simple system in weird coordinates, and we wanted to relate it to a complicated system in normal coordinates. So if in the middle, the one in the middle, we can reformulate the thing in the middle in such a way that it has absolutely no relation anymore to the structure of space and to the choice of coordinates, then it's easy to project to both sides. That's why we want to get rid of the metric, and that is quite easy. Well, the only thing that I have to do is I take the magnetic inductance, and instead of a vector, I define it as a matrix. And how do I do this? I multiply by a completely antisymmetric object with downstairs, and here, for those who are not familiar, here you see how this is done. Here is a vector, and I can map this vector onto an antisymmetric matrix. This is a completely covariant step. Mathematicians relate this to the so-called Hodge-star operation. So everything that can be formulated with this can be formulated with that. I do the same with D. I reformulate the Maxwell equations. I will not go to the details, but miraculously all the traces of the metric disappear. This is a well-known fact that if you have this gradient of a vector, if you Hodge-star it, then the metric disappears, because the metric here would only the metric-dependent parts of the covariant derivative would only appear if J and K are symmetric, but they are antisymmetric. Thanks. Sorry, not J and K. I and J, or I and K. But they are obviously antisymmetric due to the IJK. Okay. So the statement is, in terms of these new fields, the Maxwell equation and the constitutive relation are independent of the metric, and this is the basis of transformation optics. So I can solve the Maxwell equation. I can write down the solution of the differential equations. This differential equation does not know anything about the structure of space or the choice of coordinates. And now, how does it work? Now it's fairly simple. Start with electrodynamics under known conditions. Solve the Maxwell equations in your preferred normal coordinates, Cartesian, cylindrical, spherical, whatever you like. Apply a coordinate transformation to obtain the solution in weird coordinates. Everybody knows how to do coordinate transformation, that's not a big deal. You get new solutions, which of course have the same physical content. Here is represented with a bar. Now, since the Maxwell equations are pre-metric, the solution, as I said, does not know whether it belongs to this known condition in weird coordinates or to the weird complicated condition in normal coordinates. It's just the same thing. And therefore, just reinterpret the transformed solution as the solution in normal coordinates with weird medium. So replace x bar by x, but keep the bar over the field. That's important, huh? Keep the bar over the field. And that's it. And now you have to look at the constitutive relation in the end. Permittivity and permeability tensor, due to our reformulation of D and B as matrices and no longer vectors, now became 3-index objects. And here, if you look, this is now the free space relation in weird coordinates, the free space relation in weird coordinates of permittivity and permeability. And what you see is this I obtained because I multiplied by E, and then here you see a metric. This is the metric in weird coordinates that says that the original simple system in weird coordinates is just E is essentially equivalent to D, and B is essentially equivalent to H. I have to raise and lower the index, but otherwise. But realize that if I am now in the case where I have the complicated medium in normal coordinates, this object here is no longer the metric, because this is the metric in weird coordinates. But now I'm talking about a complicated system in normal coordinates, so that is no longer the metric. So indeed, I did something. I did something to the material. So, and actually I'm coming to the end. What transformation optics is? What it is, the solution of the Maxwell equations is deformed geometrically on the basis of a coordinate transformation. The exact solution of the Maxwell equations in the medium and the medium parameters of the transformational medium are obtained algebraically. I don't have to solve any differential equations, except at the beginning the differential equation of the simple system, of course, but these solutions we already have. It's in any textbook. Transformation optics works like a coordinate transformation where we consider that the field lines are stuck to the coordinate lines. That is the simplest way to think about transformation optics. I just pull on a coordinate and the field follows with the coordinate transformation. Transformation optics can be applied to any situation and not just to the free space solution, and that is a very important difference of transformation optics to analog gravity. In transformation optics, you don't need any metric, you don't need anything that resembles any of the geometric ideas that we know from general relativity. Actually, you can play the game of transformation optics with media that do not even allow the propagation of electromagnetic modes. It's possible. It's perhaps completely useless, but it's possible. So it can be linear, non-linear, local, non-local medium, absolutely no restriction, works with anything. The transformation, this is a very important point that I could not explain because it's technically a little bit more involved. If the transformed coordinates are continuous everywhere, transformation designed interfaces are automatically reflectionless. What does it mean? It just means I don't want to have a weird medium everywhere, so I won't have my device and surround it by, for example, in electromagnetism, free space. Now I have my wave coming in here, I have my transformation that guides light around in a funny way. But this is useless if the wave that is coming in is getting reflected. For example, if I have a cloak and I want to cloak part of this object inside, but the cloak itself reflects to the outside, then of course the cloak doesn't work. And therefore it's important to have all these interfaces reflectionless, independent of polarization and incidence angle. Transformation optics automatically does this for you. And the words of warning, what it is not. The original configuration and the transformation optics medium are not physically equivalent. And the Maxwell equations are mapped exactly, but this does not apply to all physical quantities. That's the same statement in essence. Of course, if it was physically equivalent, everything would be mapped. And of course, if it's not physically equivalent, there must be something that are not mapped. And what is not mapped correctly is notably the stress-energy momentum tensor. So as soon as you talk about energy, about momentum, about the Poynting vector, these things are not mapped correctly. If interpreted as a frequency-independent method, transformation optics can yield physically nonsensical results. Well, that's rather simple, because think you have a slab like this, and in transformation optics I make it like this, then you need superluminous speed of light, inside your slab, and if it's frequency independent, you break causality. So you have to be careful. You can do things that become nonsense unless you interpret this as a single frequency method. And probably the most important drawback, TO is theoretically very powerful, but the fabrication of complicated TO media is far from easy. That's it.